Mr. Satish Chandra Ayla, he is COO, Slab Track Business Function for Mrs. Patil Rail Infrastructure Limited. He is a postgraduate in civil engineering, has extensively worked for more than 25 years on PSC RCC bridges and on NHAI projects before taking up the career on railway engineering, mainly on ballastless track. He has worked with Mrs. Reliance, L&T on various metro projects, handling the total ballastless track suitable for different speeds and completed them successfully. Now, as head of the slab track division for Mrs. Patil Rail Infrastructure Limited, he has been promoting precast technology for use on ballastless track, meeting the requirements of different speeds and axle loads. Precast Plinth is one of such solution that is primarily best suited for solution for metro projects having speed potential of 100 kmph and axle load 18 metric ton. This is what his thoughts are. So today's topics will be related to that. So Satish will be speaking on use of precast plinth type ballastless track for metro railways. So over to you, sir.
So I'll be taking you through a small presentation on the use of this ballastless track technology that is being made with precast. So I'll just start with my presentation. So my topic would be this presentation on the precast plinth that's being promoted by us at Patil Group. So the track construction with precast plinth, actually the punchline is for better quality and for faster progress. So this will be the flow of my presentation. So I'll give a brief introduction about our company, Patil Infrastructure. Then the concept of this plinth manufacturing and the advantages of a precast plinth over the in situ system that's being adopted in the country as of now. And the tests, what all we conduct on the precast plinth and some provenness and the maintenance issues. So we Patil Group actually are based out of Hyderabad, and we have various branches pan India, and we are mainly into the track component manufacturers. So we are into urban metros. We make components for the ballasted track, and of course the ballasted track, the new technology that's being adopted for the high speed lines and the metros. So these are some of the business sectors where all we are present. So we are mainly into the production of sleepers. So Patil Group produces 60% of the sleepers required for Indian Railways through its 15 factories spread across the country. We also produce composite sleepers. These are the sleepers that are made of rubber, which are mainly used for the steel girder bridges. We also make the track components, the fastenings which actually hold the rail with the base slab or with the sleeper, which we call as fastenings. So we produce the ballasted and ballastless fastenings. And of course, we have different types of ballastless track solutions for station aprons, for urban metros, and that is including the viaduct and tunnels, which I'll be talking further on this presentation. We are also making the HTS wire, the high tension wires, which are required for use in this sleepers as a part of backward integration. We also make the inserts that actually again a part of a sleeper, which holds the rail with the sleeper. We supply ballast. We have different crushers at various locations. The supply of ballast is also done by us. The flashbed welding, we produce the Patil Rail Infrastructure Limited, we produce around 3,000 welds per month for Indian Railways. We have two flashbed welding plants, one in Assam and one in Hyderabad. We also offer engineering and technical supervision for all the business. So these are our presence. So as I've told you, these are all the factories wherever we are located. And we also have the wire plants and the components for track also produced at different locations. And we have a strong design team sitting in Hyderabad as well as in Delhi. So I'll just get into the main subject. So for my colleagues actually who are not well versed with what ballasted and ballastless track is, to just throw some light on that, I'm just showing this slide. The track is also called as permanent way, a railroad which together with the points or crossings or we call the turnouts, they guide the trains without the need for steering. And it consists of mainly two rails having specified distance, what we call the gauge. And this actually are fastened to the sleepers, which are embedded in a layer of ballast, the one you see on the left-hand side, having a specified thickness over the formation, which we call it a ballasted track, which we see on the Indian Railway network. The other one is a ballastless track, where actually the rails are fixed with these fastenings to the concrete bed. So this is a ballastless track. So ballastless track is a topic for the day. And going further, ballastless tracks has been proved to be very alternative to the conventional track with ballast. And because of its advantages, it has entered the country 2 decades ago. The conventional ballastless track or the concrete slab track, what we call, are generally in cast institute types in which the precast concrete members are embedded in the cast institute concrete. It's a combination of the concrete member getting mostly into the majority of the in situ concrete. But there are various defects and there are a lot of post-concreting works that are required in this cast in situ ballastless track. And there's a lot of time and labor involved that has led to the use of this precast technology in ballastless track. So I'll just speak about the different, there are number of ballastless tracks available in the world, but I'll speak about the very few which actually we are also promoting in the country. The first thing is the precast plinth. You can see a beam over here, over which the rails are fixed and fastened to the plinth along with that. And the next one is a pour slab. Pour slab actually is a slab. So this is actually a 4.2 by 4.2 meters by 2.4 meters slab that actually is precast and is taken onto the viaduct or into the tunnel and fixed onto the viaduct, and over which the rails are fixed. And we have one another system called the Patil radar system. Here you see this actually is a sleeper. This sleeper is a bi-block sleeper. So this is actually one block under this rail. It's another block under the other rail. These are two integrated with an exposed concrete. And mainly this has a lot of in situ concrete that needs to be poured. Even though it's ballastless track, the amount of in situ work is very much over here. The fourth one I'm talking about is the J slab. The J slab, now we already have heard a lot about our the bullet train project that's going to connect Bombay and Ahmedabad. So this is the slab. This again is a 4 meter by 2.4 meter or 5 meter by 2.4 meter slabs, which are precast, brought onto the site and integrated with the base concrete. So a precast plinth is a reinforced precast segment. It's not a post-tension or pre-tension. It's a reinforced concrete segment having around 6 to 7 rails. So these are called the rail seats. Where the rail actually is fixed onto the concrete is called a rail seat with some openings in between. That is for a standard plinth. This mainly is to stitch the concrete with the base concrete. So this, by pouring the self-compacting concrete through these openings, this precast member is stitched onto the base concrete either to the tunnel bed or to the viaduct. And with this being a reinforced concrete member, the reinforcement below the foot of the plinth and in the blockout. So we have some reinforcement in the blockout also, the openings is kept exposed so as to have a better bonding between the precast and the in situ concrete. So this is the base of the precast plinth technology. And depending upon the radius of curves, so we have different radius of curves and tangent tracks. So the standard plinths will be approximately 3.4 to 4 meters, and they actually are very good for use on vertical curves having a radius of 1500 meters. And because of having this 3.4 meter plinths, it will be able to manage all the design track parameters, even the curved sections, along with the straight tracks, or also called the tangent tracks. So we need a minimum height of around 40 mm below the plinth, the bottom of plinth or the top of the deck slab or the top of the invert level of the tunnel for stitching, better stitching between this concrete member, the precast member and the in situ member. And we also actually have the bonding into the deck from the openings. So wherever actually we need to integrate, we also make some drills into the existing concrete of the viaduct to make it more integrated, which we call shear connectors. The height of the plinth, so because now the requirement of the height of the plinth varies on different parameters. So we take the as-built levels of the deck, and the height of the cast into plinth is decided based on that. So if the grouting requirement is going beyond 100 mm, generally it's ideal to keep it around 40 to 50 mm. So if it goes beyond 100 mm, then what we need to do, we need to, the exposed reinforcement that is left at the bottom of the concrete plinth will be extruded and tied to the shear connectors that are already drilled into the viaduct or the tunnel to make it more monolithic with the bottom concrete. And these are some technical specifications about the plinth. So generally the grade of concrete will be M45 and the number of rails is I've already told you it will be around 6 and the standard length will be around 3.45 to 4 meters. And the minimum thickness at the rail seat, under the rail, the minimum thickness of the concrete precast member will be around 150 mm and the self-compacting concrete will be generally of M40 grade. The openings will be around zero point 0.3 by 0.15 meters in size, and the distance between the rail seat to rail seat, that is the fastening to fastening distance where it is anchored onto the plinth, will be around 600. And in general, the weight of the plinth is around 1 meter for this 3.4 meter, 45 meter plinth. it's generally 1 meter. In the fastening system, even though we can go with different types of fastening systems, we ideally feel that the system 301W, which actually is developed based on a German design, is ideal for this type of precast members. If you see the amount of concrete that's being poured, generally half a cubic meter of concrete will be the requirement per meter length of any precast plinth. So by using this precast plinth, 0.35 cubic meters is precast, and only the 0.14 cubic meters of concrete will be used to be poured at site. And the weight of steel which will be required would be around 55 kgs per track meter. So this is a drawing which shows about the cross section and the plan of the plinth. You can see these are the openings over here, and these are the rail seats, and this is how the cross section looks. So this is the steel member, the rail member on which the train moves, and it is mandatory as per the requirements of Ministry of Railways that we need to provide a guard. So this is a concrete derailment guard which you see around 200 mm, and it is actually has to be provided a distance of 210 mm. This is a requirement of again the Indian Railways that we need to provide this. So that actually the purpose is in case the train derails, the train instead of actually falling off from the viaduct, it is caught in between this rail and the concrete member, and it avoids a bigger damage to the viaduct or falling off the train from the viaduct onto the road. So this is also provided in the precast plinth member. And this is how this is another design. So whether if you don't have the shear connectors coming out of the base concrete to make it more integrated, we have a bigger openings where these dots are the shear connectors that are drilled onto the viaduct. In case the shear connectors are already provided in the viaduct, so the shear connectors actually are made in such a way, the precast plinth is cast in such a way that it gets integrated with the shear connector that is coming from the viaduct. And once it gets integrated, the viaduct and the precast plinth becomes monolithic and will work together for the safety of the running of trains. This is another cross section showing about the reinforcement details. So as I've told you, they will be requiring around 55 kgs of reinforcement per meter of plinth. In case actually we have the very sharper curves, again there's a requirement that we need to provide a restraining rail. So a restraining rail is a third rail. So we have two rails. So you can see one more rail. This is actually in the form of a C. We call it check rail also in some places. So the idea is whenever the train is negotiating a sharp curve, so there are so much of centrifugal forces that get generated, and to resist all the centrifugal forces from one wheel would become difficult. So this check rail is provided for the inner track so that the back of the wheel gets in contact with this check rail and it balances the centrifugal forces. So this actually is also a requirement of Indian Railways, and this is mandatory for all the metros wherever the radius of the curves is less than 190 meters. So the precast plinth, wherever there's a requirement of putting this 33C1 rail, the plinth instead of 750 meters, which generally is a standard plinth, becomes 900, and we'll be providing this check rail bracket also to meet the requirements of the negotiation of trains on the sharp curves. This is how you can see the precast plinth on a straight line. So these plinths actually are around 4.35 I told you, and these are discrete, and there's an opening that is left between each of the plinths. So the advantage of this actually, whatever water that is getting accumulated on these sides will be diverted onto the center, from where actually it is taken on towards the pier and is drained off from the viaduct. So on the curves, we have a shorter plinth, as I've already told you. The shorter plinths will be around 1.75 meters to take care of the parameters. And again, these are also discrete, and we have the openings kept so that there is no retention of water on the viaduct, and there will be free flow of water from both the sides of the rail to the center, and from there to drain off comfortably. Now I'll just take you through a few slides that speak about the construction of the manufacturing of this precast plinth. So the precast plinth, this is a reinforcement cage, how it is made. Then this is the mold. The cleaning of the molds takes place, and it's cleaned with compressed air and demolding oil is applied. And after that, the cage is lowered. And here you can see the precast plinths are cast inverted. So if you see the member over here, so this is how the precast plinth looks. But if you see the casting, at the casting, this actually becomes the bottom. And this will be so this comes at the top and this comes at the bottom. It is cast inverted. So this is what you can see. This is the bottom of the plinth when actually it is standing for erection. So once the reinforcement is installed, the openings, the boxes are installed where actually this will work as openings for this concrete plinth. Then after the concrete is poured, and vibrate it. It's the usual process. And depending upon the height, so we have different heights that needs to be taken up. So ranging from 150 mm to 300 mm, that will be the depth of the plinth. So depending upon the site requirements, we measure that, and the reinforcement at the bottom is left out, which actually, as I already explained, will get integrated with the shear connectors that actually gets projected from the viaduct. So once that is done, then it goes for curing. So it goes for a steam curing. And after 12 hours of steam curing, they are demolded. And once they're demolding is taken, then they are stacked in the stack yard. And this, once they are stacked, they are ready for dispatch to the site. So these prints can be taken on the normal trailers. We don't need any special requirement since the weight of each print is already hardly 1 ton. So they are loaded onto the trailers, and from the manufacturing location, it is taken to the location where it needs to be installed. So now, once it is brought to the site, now the next process involved is a track installation procedure. Now, these points I'll just show you by way of pictures. That will be more easier for a better understanding for every one of us. So here, the preliminary survey is taken up, and then once the survey is done, the location where it is allowed to take on to the viaduct. So there, the heavy crane is installed, and from the trailer, the concrete members, the precast members are lifted and kept on the viaduct. I'm giving an example of viaduct over here. So it is lifted, and at that location, the precast pins are taken onto the viaduct. So once they're placed on the viaduct, then we have a mobile gantry. You can see on the right hand side, this yellow thing is the mobile gantry, which will be running on pneumatic tires, or it will be also made to run on the temporary rails that are made to rest on the top of the viaduct. So these temporary mobile gantries lift the plinths, and they travel on the viaduct and take it to the location where it needs to be placed. So once they are taken onto that location, they are made to rest on the viaduct. And after that, the installation of the fastenings. So these are called the fastenings. So these fastenings actually are made to rest on this precast plinths. So once the fastenings are fixed onto the plinth, then the rail, which is already kept, which is welded and kept, will be made to rest on, will be brought onto these fastening systems. Once the rail is brought onto this fastening systems, it is tightened. The moment the rail is tightened with the fastening system, the rail, the fastening system, and the plinth actually everything becomes integrated. And now these yellow things we call the gauge support frames or the spindles. So these members are kept under the bottom of the rail, and they are lifted. So here in all the ballastless track technology, we call the top-down construction. That means the rail is the member on which the train runs. So we bring the rail to the final line and level. So once the rail is brought to the final and level, and when it is lifted with the help of the jigs, then whatever gap is created at the bottom is filled with the concrete. So here you can see the jigs actually have been placed, and the rail is brought to the final level, and the plinth is hanging from the rail with the help of the fastenings. And we do the pre-adjustments of the alignment and the level that's required. And now you can see just a picture of the shear connectors. It's animation of the shear connectors, how a viaduct looks. So under every rail, we have two shear connectors. So this is one rail, this is one rail. So this is completes one track. And this is for the other track. This is for the track going towards upline. And this is for the one coming to the downline. Now, once the plinth is kept, the bottom reinforcement is made to tie like this with the shear connectors. So once it is tied to the shear connector that's already projecting from the viaduct, it becomes a monolithic and becomes an integrated member of the viaduct. So this is how the member looks once it is placed on the viaduct. Now, once the final survey is done, we do the installation of formwork. The formwork at the bottom of the bottom of the plinth, minimum 40 to 60 mm is the concrete that needs to be filled up as a stitch concrete. So the shuttering is placed. Then we do the final survey and adjustments again to check to see that the final liner level is accurate. Because the main disadvantage of ballastless track is since actually is going to be fixed in concrete, so we cannot do any post adjustments. So any adjustments that need to be done, the entire parameter set should be brought to the 0, 0 level prior to the concreting takes place. So once the final survey is done and the adjustments are fixed, then the concrete is poured through these openings. So we have the self-compacting concrete that poured, and a minor vibration is done. So once this is done and the pouring of concrete is done, then that's it. So we remove the shuttering, and once the concrete, the stitch concrete, whatever is poured gain strength, the track is ready for service. So we do not have any other works. Like there are many other works which I'll explain to you, which needs to be taken up when we do with the cast sensitive concreting. So we can see a photograph of the completed tangent track, and this is a completed a curved track with the precast plinths. So you can see how clean it is. There's no dirt or there is no any unwanted material kept on the viaduct because of this. Whereas in the cast in situ systems, there are many other things actually that needs to be done before the track is brought to service. So I'll just make a small comparison between the precast and the cast in situ systems. If you see over here, now this is a photograph, a live photograph that has been taken with the precast, with the cast in situ. Here, everything right from the tying the reinforcement to pouring the concrete and a lot of the rear works or the post works, post concreting works, everything has to be done outside. So you need a lot of labor and machinery to do all this. You can see the work is going here in the precast system. The entire work, whatever has to be taken at place in the site, is done in the factory premises under the controlled atmosphere, maintaining the quality. And of course, it gives a better aesthetic finish also. Large amount of concreting needs to be poured at the site, whereas hardly 1/10 of the concrete needs to be poured with the precast system if used at with the precast system, which actually is becoming a bigger problem in urban scenarios, mainly for the metros, where getting a traffic block to pour the concrete is becoming a challenge nowadays. Now, after the concreting is done in the cast center system, there is a lot of work. We call it rear work, or there's a lot of post concreting works. The entire work after the concrete is poured, we need to remove the rail, we need to remove all the fastenings, we need to attend to the concrete. Then once it is attended, then again we have to bring back all the fastenings, all the rails into the system. Then we need to tighten it for bringing it to service. Whereas we don't have any such thing. As I've already explained, once the concrete gains its state, the track is ready to take the service loads. So this saves a lot of time and labor. And you can see the amount of debris that gets generated in the cost sensitive systems. There's a lot of material that gets lifted onto the viaduct. Again, this entire material has to be brought onto the ground, which needs again block traffic block, and that which actually is the biggest problem in the urban scenarios. Now, coming to the precast, the finishing is quite good because everything is done in a controlled atmosphere. So you can see the photographs, it speaks everything, how the concrete finish is there in the site, in the in situ system, whereas the finish that is done in a controlled premises like a factory. Now, if you see a comparison, the main thing I'll just take one or two things. We have good quality control because the entire thing is done in a casting yard. The appearance is very good because it's controlled. There is no rear work. I've explained to you the rear work actually takes a lot of time, whereas that is mandatory in the casting system. Main thing in the cast institute system, we need to wait until the last work of the civil work is completed. Like the viaduct has to be completed in all respects, including the installation of the expansion joints and the parapets. Whereas in cast precast, the casting of plinths can go parallelly, and you do not have to wait for the civil works to get completed 100%. So the advantage of this, it is always offline, and it's in using a precast system, it will be not on the critical path. Whereas once the delays are happening on the viaduct or on the tunnel installation, the entire pressure, entire delay gets transferred onto the track system. Then another table just showing, because if you take a 1,000-meter track, taking from my experience, whatever installation we can do, if you see the entire work, there are some 6 to 7 activities that takes place in the installation of track with in situ as the or the precast plinth. If you use the precast plinth, we need around 30 days to complete the entire work in 1,000 meters, 1 kilometer. 1 kilometer of track can be made ready in 30 days. Whereas in the in situ system, we need at least 57 days because the main culprit is the rear work. If you see the rear work, the post works after concreting, they take a lot of time. They take almost 7 to 10 days, whereas there is no rear work in our scenario. And the installation also, if you take only 8 days for installation of precast plinth, it takes almost 28 days to do the cast institute. So there's a lot of time. So for 4 weeks of saving for every kilometer of track that is done with the precast system. Now, some tests that we already done, I'll not get into more details about this. These are all tests. We have done different tests as per the ERIMA standards 2002. And all the tests that has been carried out on the model of this precast plinth have successfully completed. And we have got fair good results in all the tests. So this is about the vertical load test, then some shear resistance, then the pull-out test, a very important test for railway. Then the cyclic load test, we have done 3 million cycles of cyclic load test to see the performance of the track structure. And this has proved out very successful. And this is the setup, like we apply a load of around 12.5 tons in the inclined position with the actual prototype of the concrete plinth and the rail. And we have done for 3 million cycles, and which has given us fantastic results. The advantage, again, I'll just speak about a few advantages. It's a well proven and mechanized system, and it's environment friendly. And since metro regions where urban scenarios are the prime locations where we do the metros, we have a lot of restrictions because of the noise and other problems. And whereas all these things are avoided because of using the precast systems. About 65% of concreting is cast at the site, and only 35% is at site. Productivity is very high. We can do around 100 to 125 meters per day per team, whereas it's hardly between 30 to 35 meters in cast too. Finish is much better because it's already because it's done in the controlled atmosphere. It is already possible for deliver to deliver the entire assembly with the fastening systems, whereas in situ, which is not possible. No post concreting works, compatible for all curved tracks, irrespective of the radius of the curves. Any sharp curve can be taken up with that, and we can provide a chamfering to give better aesthetics. And of course, fastening system, we have different fastening systems that hold the rail. But as I've already told you, it's ideal to use system 300, which is better for this type of precast plinth systems. It can be used for the underground as well as for the tunnel, for the viaduct sections. It can be used with the check rails I've already explained to you. We can use it for DC third traction. We have two types of tractions. We have the OHE with 25 kV. So Indian metros are also using the DC traction, where we have problems with the stray current. They're also easily manageable with the precast pin systems. And we can use the standard pins on any type of span configurations. And only the turnouts, the junctions actually are cast in too. So we have not developed any system for putting the turnouts on precast plinth. We are just developing on that. And precast system combined with the system 300 fastening system is about 5 to 10% cheaper than the in-situ systems. It has already been used. These are some of the references. It has already been used in Bangkok on the Purple Line, of course, the Gold Coast, Australia, and the Bangkok's South Skyline. And many other projects are coming up. The list of projects you can see here, the dark red line, orange line, and the other lines, Bangkok, other lines actually coming up with this precast plinth technology. As per this requirements of the technical wing of Ministry of Railways, it's clearly said that we can use the precast plinth, precast or the cast in systems. So any metro is free to choose between the cast in and the precast system. So it's already made very clear by the Ministry of Railways that the encouragement that's to be given to the precast systems. So metros are at liberty to use the precast system. There's no restriction or approval, special approval required from the ministry. And these are some of the photographs I've taken that has been done with the in-situ system, where actually that you can see a lot of damages that have occurred in surveys, which actually requires a lot of time for repairs, which again will be hampering the services, speed restrictions, hampering all the services. So all these things can be avoided by using the precast plinth. So if you use a precast plinth, it is having a lot of low maintenance, and it's better durable than the cast in-situ systems because of the advantages that has already been told about. Major issues what we are facing is actually there are a lot of repairs that happens to the cracks. The anchor bolts which gets embedded into the concrete, they gets loosened up, and they need to be fixed up. There's a lot of tilting of the anchor bolts that actually the fastenings that get into the concrete, and we need to core cut and remove it for getting the repairs done. And there are a lot of improper rail seats. The rail seat actually there'll be hollowness that is observed in many of the rail seats that actually gets broken under service. And all these things will be there'll be a lot of projections of reinforcement and corrections needs to be done in the institute system because of the pressure that people work with, because of the delays that's happened, because of the pressure they have and the tight schedules. So if you use the system, there's no requirement of this expenditure for the maintenance. We need not have to do any core cutting to do the repairs, which further will reduce the weakness of plinth, the plinth beam. And we did not require any special permissions for taking up this work, disrupting the traffic. And trains actually, as I told you, they may be made to run at restricted speed to avoid impact to these rebate conditions, which will be impacting the headway and the operations. So these are all the services of what as a Patil group will be able to provide. So we provide all the pre-bid services for all the ballastless track systems. We do the designing of the precast plinth as required by the clients. We manufacture and supply the precast plinth members. We do manufacture and supply the fastening systems, and we also give the technical support, the supervision, and the overall quality control. So as one group, as one unit, we give the one point responsibility for taking up all these services from the Patil group. So that's all from now. So thank you so much for giving me this opportunity. And now I'll just open up for any Q&A, please.
I just had a small query, in fact, on the concrete grade for the plinth and the concrete grade for the self-compacting concrete differ. You
Yeah.
mentioned 45 and 40. Why is that difference? Because generally what is practiced is that whatever is the base concrete of the precast element, the grout is or the self-compacting concrete is also of the same grade.
Yeah, see, generally we prefer to go with M40, but recently what has happened that because of the requirement to gain early strength, we actually have made it M45. But M40 for the precast print equally suffices the requirement.